If you're watching this video, you're probably familiar with machine learning. Maybe you're a data scientist who has spent countless hours tuning hyperparameters, or you're a developer wondering why your model's validation loss looks like a Jackson Pollock painting. While some of these facts might be obvious to those who dream in tensors, there are fundamental misconceptions that even seasoned ML engineers get wrong. Welcome to 30 machine learning facts that will make your neural networks question their existence. Whether you're a PyTorch enthusiast or someone who thinks CUDA is a fancy brand of cheese, you're about to learn why everything you know about ML might need a model update. Machine learning and artificial intelligence aren't the same thing, and this distinction actually matters for system design. While AI encompasses any system that can intelligently process information, ML is specifically about learning from data. Think of it this way. If AI is like the entire Stack Overflow community, ML is specifically the part that learns from copying and pasting other people's code. Deep learning isn't always better than traditional ML algorithms. Your 50-layer neural network might be impressive at parties, but sometimes a simple linear regression is all you need. Here's what happens in the real world. While deep neural networks excel at learning hierarchical representations, they often underperform on structured data or smaller datasets. Let's look at a performance comparison that might surprise you. Neural networks don't actually work like human brains. They're more like extremely organized spreadsheets that learn calculus. When neuroscientists talk about neurons, they're discussing complex biological systems. When ML engineers talk about neurons, they're really just describing a mathematical function that does weighted sums. Here's what's actually happening in an artificial neuron. Supervised learning isn't supervised by humans, despite what your project manager thinks when they ask you to supervise the AI. No, you don't need to watch your model train like a helicopter parent. Supervision in ML simply means your training data comes with labels. It's more like giving your model an answer key than actually supervising it. Parameters and hyperparameters aren't the same thing, and understanding this distinction might save your model from disaster. Think of parameters as what your model learns during training, like a student figuring out answers. Hyperparameters are what you, the engineer, must set before training begins, like a teacher designing the curriculum. And just like education, choosing the wrong learning rate, teaching pace, can lead to either boredom or total confusion. The term learning in machine learning doesn't mean machines understand anything. They're just really good at pattern matching through optimization. When we say a model learns, it's more like a very sophisticated game of hot and cold with a loss function. The model isn't gaining wisdom, it's just trying to make some numbers as small as possible. Bigger isn't always better in ML, sometimes less data is more. While everyone's obsessing over training on terabytes of data, here's a shocking truth. Many successful models work better with smaller, carefully curated datasets. It's not about the size of your dataset, it's about the quality of your features and the cleanliness of your data. Data augmentation isn't always beneficial. In fact, sometimes it can introduce subtle biases that poison your model's understanding. While flipping images and adding noise might seem like an easy way to expand your dataset, consider this. In medical imaging, a flipped tumor might represent an anatomically impossible scenario. In financial data, shuffling temporal patterns could create impossible market scenarios that your model learns as valid. Model complexity isn't directly related to model size, a concept that might save your computational budget. A model with millions of parameters might be implementing something as simple as a linear relationship, while a tiny model might capture complex, nonlinear patterns. It's not about how many parameters you have, it's about how you use them. Feature engineering isn't always needed in deep learning, but it's absolutely crucial for traditional ML. Deep learning can automatically learn useful representations from raw data, which sounds magical until you realize you're trading feature engineering for endless hyperparameter tuning. Meanwhile, traditional ML algorithms can outperform deep learning when given well-crafted features. 100% accuracy isn't always good. In fact, it's usually a massive red flag. When your model achieves perfect accuracy, it's like a student who gets every question right by memorizing the test answers without understanding the material. In machine learning, we call this overfitting, and it's the equivalent of your model becoming a very expensive lookup table. Balanced datasets aren't always better. Sometimes the real world is inherently imbalanced. If you're detecting fraudulent transactions, you don't want 50% of your training data to be fraud cases unless you're running the most unfortunate bank in history. The key is making your training data distribution match the real-world distribution you'll encounter. Missing data isn't always bad. Sometimes it's the most informative part of your dataset. When a value is missing, ask yourself why. Did someone forget to fill it in? Or did they intentionally skip it? In fields like healthcare or user behavior analysis, missing data can be more revealing than the data that's present. Outliers aren't always errors. They could be your data's way of telling you something important. In fraud detection, those outlier transactions might be exactly what you're looking for. In scientific discovery, outliers often lead to breakthrough findings. Sometimes, the most interesting patterns are the ones that don't fit the pattern at all. More layers in neural networks don't always mean better performance. Sometimes they're just better at wasting GPU time. It's like adding more layers to a cake. At some point, you're not improving the taste, you're just making it harder to eat. The key is finding the sweet spot between model capacity and actual problem complexity. Cross-validation isn't always necessary, and sometimes it can even lead you astray. While it's often treated as a mandatory ritual in ML workflows, there are cases where other validation strategies make more sense. For time series data, for example, randomly shuffling your data into folds is like trying to predict the past using the future. Mathematically possible, but practically useless. Accuracy isn't always the best metric. In fact, it can be downright misleading. Imagine a system detecting a rare disease that occurs in 1% of cases. A model that always predicts no disease would be 99% accurate but completely useless. This is why we need metrics that actually match our problem's requirements. Model interpretability isn't always sacrificed for performance. That's just an excuse for not making our models more transparent. While it's true that some complex models are harder to interpret, we have powerful tools for understanding model decisions. It's not about choosing between accuracy and interpretability, it's about finding ways to have both. Higher precision isn't always better than higher recall. This choice depends entirely on the real-world consequences of your model's mistakes. Think of it like a medical screening test. Would you rather have some false alarms or miss some actual cases? In fraud detection, missing one fraudulent transaction could cost more than investigating 100 legitimate ones that looked suspicious. Ensemble models aren't always better than single models. Sometimes they're just a more complicated way of being wrong. While combining models often helps, blindly throwing more models at a problem is like hiring multiple people who all make the same mistakes. The key is ensuring your ensemble members make different kinds of errors, bringing genuine diversity to the table. Model confidence isn't always reliable. Your model can be very confidently wrong. Just like that friend who's absolutely certain about everything they say, high confidence doesn't equal accuracy. Modern ML models, especially deep neural networks, tend to be overconfident in their predictions, which is particularly dangerous in high-stakes applications. Machine learning models don't always need to be retrained. Some can stay effective for years. While the tech world loves to push constant updates, sometimes stability is more valuable than chasing marginal improvements. If your data distribution isn't changing and your model is performing well, retraining might just be introducing unnecessary risk. Cloud deployment isn't always better than edge deployment. Context matters more than conventional wisdom here. While everyone seems to be rushing to put their models in the cloud, sometimes keeping inference close to the data source isn't just more efficient. It's absolutely necessary. Think about autonomous vehicles. They can't afford the latency of sending sensor data to the cloud and waiting for a response about whether to brake. AutoML isn't always better than manual tuning. Sometimes, it's just automating the process of building a suboptimal model faster. While AutoML tools can be incredibly useful for rapid prototyping, they often miss domain-specific optimizations that an experienced data scientist would catch immediately. It's like using autocorrect for programming, helpful for basic tasks, but you wouldn't want to use it for building critical systems. Transfer learning isn't always beneficial, even though it's often treated as a magical solution for small datasets. The intuition seems compelling. If a model has learned to recognize cats and dogs, surely it can help with recognizing medical conditions, right? But here's the crucial detail. Features learned from one domain don't always translate meaningfully to another, and sometimes they can even lead us astray. ML projects don't always fail due to technical issues. More often, it's because of organizational and communication challenges. You might have the most sophisticated model in the world, but if stakeholders don't understand its limitations, if data scientists and business teams speak different languages, or if the problem itself isn't well defined, your project is headed for trouble. Neural networks aren't complete black boxes. That's just become a convenient excuse to avoid explaining them. While it's true they're complex, we've developed sophisticated tools and techniques to peer inside these networks and understand their decision-making process. From attention maps to feature visualization, we can actually see what different layers are detecting and how they build up to final decisions. Data privacy isn't always compromised in ML. We've actually developed powerful techniques to train models while protecting sensitive information. From federated learning to differential privacy, we can now build powerful models without directly accessing individual data points. It's like being able to learn from a crowd without ever having to identify any individual in it. Model bias isn't always bad. In fact, inductive bias can be crucial for learning. When we talk about bias in ML, we need to distinguish between harmful societal biases and helpful inductive biases. Inductive bias is like your model's set of reasonable assumptions about the world. Without it, learning would be nearly impossible. Think of it as the difference between prejudice and prior knowledge. Machine learning models don't always need regular updates. Stability can be more valuable than chasing minimal improvements. The continuous update mindset borrowed from software development doesn't always translate well to ML systems. Sometimes, a well-trained model that's stable and reliable is better than one that's constantly changing and introducing new uncertainties. Machine learning isn't about following a fixed set of rules. It's about understanding the nuances that make each problem unique. The field is filled with apparent contradictions. Sometimes simpler models outperform complex ones. Stability can be more valuable than constant updates, and what works in theory doesn't always translate to practice. What matters isn't memorizing a set of best practices, but developing the judgment to know when to apply them. Every ML problem exists in a context, and success comes from understanding that context deeply enough to make informed decisions. The most powerful tool in machine learning isn't the latest algorithm or the biggest dataset, it's the ability to think critically about our assumptions. Keep building, keep questioning, and most importantly, keep learning. If you found this video helpful, share it with someone who might benefit from it too. Like and subscribe for more machine learning and data science content, and check out my other Python and machine learning tutorials on this channel. Your support means everything. Consider backing my work on Patreon to help create more free educational content. You can find the link in the description. Thanks for watching, and may your models never overfit.